Okay, so we're going to start off the second trigonometry unit now, and we're going to introduce the whole idea of a periodic function. Now, if you have taken the mixed math, the 3M course, you will have seen these before, but no worry if you haven't seen them before, they're not too bad. So a periodic function is any function that has a graph that repeats at regular intervals. So an example of that in terms of a parent function that we've seen before would be y equals sine x. You see there's a repeating pattern here. Every specific interval, it repeats itself over and over again. So this would be an example of a periodic function. Another example of one that you've seen before that would be periodic would be cosine x. Some other examples that you might see if you want to see some pictures here. All these graphs, again, you have a pattern that repeats itself at a regular interval. All of these are called periodic functions. Okay, now, for the most part, we're going to focus on the two parent functions that we talked about, that I just mentioned here, sine x and cosine x. And I know you graphed them very early on in the course, so you may not remember too much about them, but they are going to come into play a lot here. So just to remind yourself what they look like. Sine x looks like this. So it repeats every 360 degrees. Repeats that pattern every 360 degrees. If you're looking for key points that are on there, you may remember some of these when you're solving equations in the last trigonometry unit. So 0, 0, 90 degrees, 1, 180 degrees, 0, 270 degrees, negative 1, and 360 degrees, 0 would all be some key points on that first cycle of y equals sine x. Okay, y equals cosine x looks very similar. It just looks like a slightly shifted version of y equals sine x. And again, there's some different key points there that we're going to need to know in order to make accurate graphs today. Okay, so again, these graphs are going to be used extensively throughout this unit, so if you haven't committed these to memory yet, please make sure you do so over the next little while, because we're going to be working with these ones a lot. Okay, now a graph that is like sine x or cos x or transformation of it is called sinusoidal, but we'll talk about that coming up later. So let's just take a look at some definitions that apply to periodic functions. So the term cycle applies to the smallest complete portion of a graph that repeats. So for example, you could say a cycle goes from this point right here to this point right here. This right here would be called a cycle. Okay, now the starting point is actually arbitrary. Okay, I could start the cycle here and have it end here and have that be a cycle. I could start at the minimum point here and have it end there and have that be a cycle. It really doesn't matter as long as I'm taking the smallest complete portion that repeats, so i.e. only one cycle, not taking a cycle, for example, from over here to over here, because from that point it repeats twice. So one single complete portion of the graph that repeats is called a cycle. Okay, now the period would actually be, and this might be a term if you've taken physics before that you've seen, it's the length of the cycle in terms of the change of independent variables. So for example, going from negative 270 degrees to 90 degrees, this is one cycle. The period is how long it takes for that cycle to happen. So to go from negative 270 up to 90, that has a total of 360 degrees. So this graph has a period of 360 degrees. Okay, and if you actually look at the graphs of sine x and cos x, you'll see that's the case for all of them. So for example, you start your cycle at 0 here, the cycle ends at 360 degrees, at which point it starts to repeat. So sine x has a period of 360 degrees, cosine x exactly the same thing. So we start here at the maximum at 0 degrees, after a full cycle, starts again after 360 degrees, again a period of 360 degrees for cos x as well. Okay, some other terms, in terms of the axis here, the axis is the horizontal line that is halfway between the maximum and the minimum. Okay, so on this graph right here, if your highest value is at 1, your lowest value is at negative 1, again looking at the y values here, the axis would be halfway in between. So if I were to draw that in on here, it would occur right on the x-axis. So this would be the equation of your axis here, and in this case the equation would be y equals 0. Okay, so how can you find it? How can you calculate that? Well, just like when you're finding the axis symmetry, when we average the two x-intercepts, we're averaging the maximum minimum values here to get your axis. So in this case, my maximum value is 1, my minimum value is negative 1. 1 plus negative 1 is 0, divided by 2 is still 0, so we get y equals 0 for our axis. Okay. Next definition is amplitude, and there's two ways of looking at amplitude. It's either half the distance between the maximum and the minimum. So looking at the graph here, my maximum is at 1, my minimum is at negative 1. Okay, so that full distance between them is 2, half that distance is 1. So this particular graph has an amplitude of 1. The other way you can define it instead, you can look at the distance between the axis and the max or min. So if the axis is at 0, the distance from the axis to the maximum is going to be 1, or the distance to the minimum will be 1 as well. Okay, two ways you can calculate that. You can take your maximum value, subtract your minimum value, and divide by 2. Or if you have your maximum value, you can subtract the value of the axis from there to get your amplitude. So two ways of calculating that one. And the other thing I want to note here, the amplitude is technically a distance, so it cannot be negative. Okay, it's a physical distance. So even if, let's say, you're counting down from the axis down to the minimum here, this is a distance of 1. You wouldn't say it's negative 1 even though it's going down 1. The overall amplitude here is 1. Okay, so those are all the sort of new terms that are going to come up with periodic and sinusoidal functions. So again, I briefly showed these pictures before. These are examples of other periodic functions. They repeat, but they're not called sinusoidal. Now, a sinusoidal function, if you're looking for the official definition, is one that would be a transformation or a transformed version. And it would be a transformation of one of the parent functions we've seen that's either sin x or cos x. Okay, so if it's a transformed version, so it's been stretched, compressed, shifted left, right, up, down, that's okay. That would be called sinusoidal, and it would still be periodic. But these particular graphs right here, while they are periodic, are not sinusoidal because these are not transformed versions of sin x and cos x. Okay, just keep that in mind. So all sinusoidal functions are periodic, but not all periodic functions are sinusoidal. Okay, so some other things to remember, going back to Unit 1, when we first looked at transformations, if I'm doing just a general transformation of a function f of x, so I have f of bracket k times bracket x minus p plus q, just stating all your transformations, remember that a is your vertical stretch or compression, and potentially reflection if a is negative. K told you a horizontal stretch or compression, potentially reflection across the y-axis. And P and Q was your horizontal and vertical translations respectively. And what we're going to start doing now is applying all these concepts from the first unit into transformations of y equals sine x and y equals cosine x. So let's try and look at that. So now if f is sine x or cosine x, what are the transformations going to be? Okay, let's take a look at them on a graph. Okay, so here's a graph of y equals sine x, and you see I've kind of set it up so I have different sliders so I can change the values of a, k, p, and q. So let's take a look at a value. Now, if that represents a vertical stretch, let's see how that changes the graph. So it seems to make it bigger, okay, so which would sort of be what you'd expect. Again, it's getting more vertically stretched. So what feature of the graph do you think that's going to affect? Well, it changes definitely my maximum and minimum values. Okay, those have definitely changed a lot. And if my max and min values have changed, my axis hasn't moved. It's still sort of centered, if you want to call it centered, with maxes at 0. But it's definitely gotten to the point where my maximum and minimum have moved further away from the origin. So what does that affect? That's going to affect the amplitude of my graph. How does it affect it? Well, we'll see later on. We'll make more connections between the transformations and the different features. But right now, we can see that A affects the amplitude. Okay, let's see what happens when we change K. So let's bring my A back to normal here, and if I change K, the vertical compression or stretch, horizontal stretch or compression, what does it change? Well, it definitely takes less time to go through an entire cycle if it's compressed, and more time to go through a cycle if it's stretched. So what's that going to affect? Well, it affects how long a cycle is, so that affects the period. Okay, and how does it affect the period? Well, it actually turns out that the period is going to be 360 degrees divided by whatever your k value is. Okay, and once we do a bunch of examples, you'll be able to make those connections yourself. And then also, if we want to solve for k, we can multiply both sides of the equation by k, divide by the period. So k be 360 degrees divided by your period. So if you have your k value in the equation, you can solve for the period. If you have the period, you can solve for the k value. Okay, P and Q, now again, these are your horizontal and vertical shifts. So you'll see that if I'm moving it left to right, it's not changing that much right now, but if I were to keep going, it would keep moving it a little bit more. So that just moves it left to right. We call the amount it moves left to right on a trigonometric function, we call it a phase shift. Okay, so again, it doesn't change the overall shape, but again, you're just shifting it left to right, and we call that a phase shift. And last but not least, the Q, if I change that, you'll see that moves the entire graph up and down. So what does that change? Well, yes, my max and min are moving, but you see the axis where the line halfway between your max and min is always shifting as well. It's shifting with that. So what does that change? It changes the axis of the curve. Okay. Now every graph that I've done so far, as every transformation I've shown you has been a transformation of sine x. It works identically for cosine x as well. So you can take all of these, whatever the effect on sine x, it also affects on cosine x as well. Again, we don't necessarily know how exactly A affects the amplitude or how Q affects the axis, but we'll see that coming up. Okay, so now what I'd like you to do is take a look at this graph here, and I want you to find all this information: the equation of the axis, the range, the amplitude, and the period. Okay, so if I want to start with the axis, there's two things I could do. If I have the graph, I can eyeball it. So on the graph, it's going to be halfway between my maximum and minimum. My maximum is at 7. My minimum value is at 3. So halfway between, I can even count up, will be at 5. So if I want to, I can even sort of draw my axis on here. It's going to be at y equals 5. Okay, the other way I could do that, I could do the calculation instead. So I could say my axis is going to be my max plus my min, all divided by 2. My maximum value, again, is 7. My minimum value is 3. 7 plus 3 divided by 2 gives me 5. Okay, so the range, remember the range is all the possible set of y values here. And we already kind of talked about what the max and minimum y values would be from the equation of the axis part. So if I have that, I can determine my range. My smallest value is 3. My highest value is 7, so my range will be everything, well, y can be anything between 3 and 7. Okay, for my amplitude, again, two ways I can do it. I can look at it from the graph, or I can calculate it. So on the graph, I can see, okay, it's the distance from my axis to either my max or my min. So my axis is at 5. My maximum value is at 7, so that's going to be a distance of 2. So my amplitude is 2. Okay, the other thing you could do if you want to calculate it, y would be, or sorry, not y, your amplitude would be equal to your max minus your min divided by 2. Okay, so that would be 7 minus 3 over 2, which again is 2. Okay, and last but not least, let's take a look at the period. So to find the period, we need to isolate an entire cycle from the graph. And again, where you start and finish is up to you. You usually want to try and make your life easier. So if I'm going to isolate a cycle, I see here that I have a maximum value here, and the next little peak is over here. So this right here is one cycle. The length of this cycle is going to be the period. So it starts here at 30 degrees, and it ends here at 90, 120, 150 degrees. Okay, if I use the scale of the graph. So 150 degrees minus 30 would be 120 degrees. So it takes that long to go through one complete cycle before it repeats. Okay, so let's try and make our own graphs. Okay, so what I'm giving you here is a transformed version of the cosine function, and I want us to graph one cycle of it. Now, just to think about how we're going to go about doing this, we're going to go, now eventually I'm going to show you a shorter way, but remember one of the ways we did graphs way back in Unit 1 is we started by creating a mapping rule that went from the parent function to your transform function up here. So start by creating a mapping rule. Then we took key points from the parent function and then found the transform points using the mapping rule. So we're going to have to continue this in part 2, but start by creating a mapping rule and see what you can come up with. So remind yourself here that cos x is my parent function. So if I want to create a mapping rule, I have to look at, again, both my x and y coordinates separately. This will be a good review for you, see what you remember. So the y part's easy. I look at what's happening outside the function. So the function is multiplied by -3 and we add 7. So it's -3y plus 7. And for x, everything happens in reverse, or using the inverse. So here, if you look inside the function, right now I have x, then I subtract 40 degrees, and then I divide by 2. Okay, we're going to continue this in part 2. We'll see you over there.